So, very good evening, everyone, and welcome to the NPTEL's ninth live interactive session on the course Mechanical Behavior of Materials, Part 1. The course instructor for this course are Dr. Sushank Shekhar and Dr. Sudhanshu Shekhar Singh from the Department of Material Science and Engineering at IIT Kanpur. And myself, Shivam Jaiswal, I am a research scholar in the Department of Material Science and Engineering at IIT Kanpur. So in this live interactive session, we will be going to solve some concept-related problems based on the weekly content, which will in turn will help you to solve your weekly assignment. Okay. So in this today's live interactive session, we will quickly recapitulate what are the things we have seen in week 9, then followed by some concept-related question, and if the time permits, we'll try to solve assignment 9 as well. Okay. So let's begin. So coming to the recap of week 9. So week 9 we begin with the concept known as the strengthening mechanism. So what is strengthening mechanism? So in this we have seen the methods of strengthening, like how we can increase the strength of the material by restricting the movement of dislocation. So if we restrict the moment of dislocation, definitely we'll get the higher increase in the strength. So the dislocations can interact with the other dislocations as well as grain boundaries or solute atoms or precipitates or dispersants, and which will in turn will help you to increase the strength of the material. So let me write down. Increase in strength by restricting the movement of dislocation. Okay, so the dislocations can interact with so the one way the dislocations can interact with the is other dislocation. And this mechanism is also known as the strain hardening or work hardening. The second way by which the dislocations can interact is with the grain boundaries. Okay. And this mechanism of increasing the strength is known as grain boundary strengthening. The third way that the dislocations can interact are with the solute atoms. And this mechanism is known as solution strengthening. The fourth way that it can interact with the precipitates. Precipitation strengthening. And the fifth one is solids are known as dispersion strengthening. Okay, so these are the some ways through which the dislocations motion can be restricted and which will give us the increased strength. Okay, so now let's see the first one, that is the precipitation strengthening. So so the precipitates which are very fine, it can restrict the motion of the dislocation and thus they will increase the strength of the material. So if we are talking about the precipitation strengthening, so the basic criteria for obtaining such precipitation is that the solvous line that is, should decrease with the decrease in the temperature, or in other way we can say that the the solid solubility should decrease with the decrease in the temperature. So this precipitation strengthening, also known as edge hardening. Okay. So the precipitates which are very fine restrict the motion of dislocation and thus increases the strength. Okay, so then what is the criteria to form the precipitate in the material? So the criteria basic to obtain precipitates. So we'll get precipitates when the solvous line should decrease with decreasing temperature, or that is, in other word, we can say decreasing solid solubility as temperature decreases. Okay. So let's say this is one of my system. Okay, made up from two elements. This is the A, this is weight percentage of B, and here somewhere we have the beta phase. Here we have alpha plus beta and alpha plus liquid, and here we have alpha. So this is our solvous line. So the basic criteria to obtain precipitate, that this solvous line should decrease with the decrease in the temperature. So here you can see that from this point to this point here, the solubility is decreasing with the fall in the temperature. So in such system we can get a precipitates. Okay, so this is the basic criteria to obtain a precipitate. So there are some steps involved with this there are some steps are involved to get the precipitate. So what are these steps? So there are three steps. One is the solution treatment, and second one is the quenching, and the third one is the aging. So let me write down. The three steps to form the precipitates. The first one is the solution treatment, or also known as solutionizing. So what we do in solution treatment, we heat the alloy in single phase region. Okay. We hit it in the single phase region and we hold it for some time so that the previous some precipitates are there so that they can easily dissolve. So why we do this? To dissolve any precipitates. Okay. So the second one is the quenching. So in quenching, we rapidly cool this material to a lower temperature so that we can get a supersaturated solution. So quenching. Low temperature. And why is it so? So that we get a super saturated solution. So that we get a super saturated solution. And the third step is aging. Okay. So in aging, what we will do after quenching, we will heat it to a certain temperature and we will hold it at that temperature so that the precipitates can form inside a material. Okay. So if I draw the heat treatment cycle for this precipitation, so it will something look like this. So let's say here I have time, here I have temperature. So first what we will do, we will heat it. Okay. And to temperature T naught and we will hold it there for some time. Okay. So first we will heat it to a temperature T naught in the single phase region, and then we will hold it there for some time so that we get a single phase. Okay, then the second step is we'll quickly cool it, or we do the quenching so that we get a super saturated solution. So here, suppose here I am quenching it, okay, to a temperature T1. Okay, so we'll get a super saturated solution. Then again we heat it to some temperature T2 and we'll hold it there so that we can form a precipitates inside a material. So let's say this is T2. So this one is solution treatment. This one is quenching, and this third stage is aging. So if I show it here in a phase diagram, so let's say the composition C naught. First, we will heat it to a single phase region at a temperature T naught. Okay. So this is solution treatment. Okay. So this is solution treatment. Then we will quench it to a temperature T1. So then we'll quench it to a temperature T1. Okay. Then what we'll do, we'll again heat it to a some temperature so that we can form a precipitate. So here I am heating it to a temperature T2. So this is T2 so that the precipitate can form inside a material. So now this is all about the steps and how the heat treatment cycle looks for the to get a precipitate. So if we see the microstructure for this all these three stages, so it will look something like this. So let me draw again. This is A, this is weight percent of B, here somewhere we have beta, this is alpha plus liquid, this is liquid. Here on this axis we have temperature, here we have alpha, and here we have alpha plus beta. So now if we consider at a T naught at this temperature, okay, that is the black one. So okay, so let's say this is my composition C naught, and let's say at T naught. Okay, so at T naught, so at T naught it is the single phase region. So if you see the microstructure, we will be seeing only the alpha grains. So T naught, so if I draw, so we'll see microstructure something like this. That is, we will be seeing only alpha grains. Okay, this is the alpha grains, and this is only after solution treatment. Okay, this is at T naught. Then what we'll do, we'll quench it. Okay, so what will happen after the quenching? It will not get a time. It will not give a time for a bio atoms to move out. So it will form a supersaturated solution. Okay, so if I draw it at a temperature, is blue at T1. Okay, T1. So at T1, what we will see, we'll see the same microstructure, but this is also alpha, and this is after quenching, but it is super saturated. Okay, then what we'll do, we after heating, so what will, it will cross the energy barrier and it will try to form the precipitates. So we will see the precipitates inside the grain and on the grain boundaries as well. So at T2, let's say this is my temperature T2. Sorry. So at T2, so we will be seeing some precipitates inside it. So this is my alpha and this black one is beta. So this is beta or precipitates. Okay, this one is after aging. Okay, so and this is how the microstructure will look like if the we if the precipitates are formed. Okay, so this aging it can be done on material by two way. One is the natural aging, that is after quenching, leave it the material as it is, and as the time passes, the precipitates will form. And the second one is the artificial aging, that is in which we'll provide some external heat so that the process of forming precipitates become faster. Okay, so at the industrial scale, we'll not wait for the natural aging, we do the artificial aging. So the aging can be done by two ways. One is the natural aging, in which no external heat is given, and the second one is artificial aging. So in this aging, we gives the external heat. Okay, so as I have said that over the time the precipitates will form. So over the time, what will happen? There are some changes in the precipitates. So that will talk about the precipitation characteristics, like how the precipitates changes with the aging time. So the first thing is that the size of the precipitates is increases with the increase in the aging time. The second one is the distance between the precipitates changes. So suppose here if we have two precipitates, these two black dots. So as the time passes, this grows bigger and the distance between the precipitates changes. The third one is that the interface between the precipitates and matrix will also change. So what are these? We'll see one by one. So one is the precipitation. The first one is the size of the precipitate increases. The second one is the distance between precipitates changes, and the third one, that is the interface between the precipitate and the matrix, will also change. Okay. So let's say this is my precipitate, the red one. Okay, this is precipitate. So and this is the matrix, the white portion, the remaining. So this interface that I am showing in the blue will change. Okay, as the size and shape of the precipitates changes. So before going to see interface in details, I will quickly tell you the precipitation sequence in aluminum copper alloys for aluminum 4 weight percentage copper. So in this alloy, the first when the precipitation sequence is like this, that is alpha. Here we will get a solid solution strengthening followed by the GP zones and then theta double prime and theta prime precipitates, and finally we will get a theta precipitates, that is the equilibrium precipitates. So this is the precipitation sequence in the aluminum 4% copper alloy. Okay. So now let's move towards the interface. So as I have talked about that, the interface between the precipitates and matrix will also change with the aging time. So the how many ways the interface can form, we'll see. Okay. So interfaces. Okay. So let's say this is the blue one is my interface. Okay. And this black lines are my matrix. Okay. Let me write down. This black line are matrix. And when the precipitates has one-to-one correspondence with the matrix, so here it's having one-to-one correspondence with the matrix. So let's say this is the precipitates, and here the no strain is acting. So this type of interface are perfectly coherent. So these types of interface are known as perfectly coherent interface. Okay. This is the perfectly coherent. Okay. So what we can write here, that is one-to-one correspondence between precipitate and matrix, and as well as no strain is there. Okay, as these are perfectly matching with each other. Okay, so this is the perfectly coherent interface. Okay, now the second case where the matrix and the precipitates has one-to-one correspondence, but there is a small strain associated with it. So let's say this is my matrix precipitates, and this blue one is my interface. Okay, let me write down interface. This one is also interface. So in this, the one-to-one correspondence is there between the precipitate and the matrix, but the small strain. Okay, here you can see this small strain. Okay, the small strain is associated with it. So this type of interfaces are known as coherent interfaces with strain. And here the small strain is there. Okay, so this is the second type of interface. Now the third one is like so here you can see that we have the one-to-one correspondence, but it is partially, and and here some dislocations are forming here. Okay, so this type of interfaces are known as semi-coherent interfaces, in which the partial one-to-one correspondence between the matrix and precipitate will be there, and the dislocations will be formed to take up the strain that is there. So, and the dislocations formed to take up the strain. So this is my dislocation. Okay. This one is okay interface. Okay. Now the fourth one is the incoherent interface, in which there is no one-to-one correspondence will be there between the precipitates and the matrix. Okay. So let me write. So this is the fourth one. So here we have our matrix, and let's say this is my precipitates. Okay. So this type of interfaces are known as incoherent interface. So where no one-to-one correspondence between matrix and precipitates. So these are the four different types of the interfaces that we have seen in the last lecture. So then after this we have seen like how the dislocations interact, or the interaction of the dislocation. With precipitates. Okay. So the dislocations can interact with the precipitates in two ways. One is they can cut or shear the precipitates, or the second one is that they can bow around the dislocation, or they can just means what they are doing. They are just bypassing the uh, precipitates. So this by this two way the dislocations can interact with the precipitates. So let me write down. The first one is the dislocation can cut or shear precipitates, and the second one is the bowing around of dislocation, or we can call it as bypassing. Okay. So in this two way, the dislocations can interact with the precipitates. So first, let's see the shearing of precipitates, or the dislocation can cut. Okay. So shearing of precipitate. So let's see here. I have a dislocation. Okay, something like this. Okay, and here this is my precipitate. Okay, and this is the direction of the sorry. Okay, this is the Burgess vector direction. Okay, and this is my dislocation. So what it will do? This dislocation will move. Okay, to this side, and what it will do? It will shear or cut out the precipitate. Okay, so I can write. So this one is after shearing. Okay, so dislocation will shear these precipitates, and it will move this again. Okay, and this shearing will be equal to the Burgess vector. Okay, so in this way the dislocation will move by shearing the precipitate. So there are some factors that will affect the at what is means at what means what I want to say, like the factors that affect the ease of cutting. Means this ease of cutting is depend on various factors, like the coherence strength associated with the precipitate and the matrix, then the stacking fault energy, then the if the precipitates is of the ordered structure, or the and the modulus effect, and similarly the interfacial energy and the lattice friction stress. So these are the factors that affect the ease of the cutting of precipitates. So let me write down factors that affect the ease of cutting. So what are these factors? The first one is the, let's say, coherency, strain. The second one is the stacking fault energy. The third one is the ordered structure. The fourth one is the, let's say, modulus effect. And the fifth one is, let's say, interfacial energy. And the sixth one is the lattice friction stress. Okay. So, this is about the factors that affect the ease of the cutting. So then we have seen that the shear stress required to cut these precipitates is directly proportional to the root R. So this tau is directly proportional to root R. So this gives us the information that the dislocation will prefer to cut or shear if the precipitate is small and coherent. So small and coherent. So now this is all about the sharing of precipitates. Now the second mechanism that we have seen is the by passing the precipitates or bowing of dislocation. By passing up going of dislocation. Okay, when the size of the precipitates become the large, then it is very difficult to be get sheared, and this the dislocation find a way to move around the precipitates by bowing, and it will bow around the precipitates, and by this way the dislocation will move further. Okay, so let me draw the some schematics first. Let's say these are the my precipitates. Okay, sorry. So let's say these are my precipitates. Okay, and let's say this is my dislocation. Okay, let's say this is dislocation. So what it will do? So when I apply a shear stress, let's say I have applied the shear stress tau. So what will it will do? As soon as it comes near to the precipitates, it will try to bow out. As the precipitate size is large, it will not be able. It is difficult to shear that precipitate. So it will try to bow around the precipitates. Okay. So it will bow. it will go something like this. Okay, so this is the line vector. So here I can draw the line vector here, 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 and here. Okay, so as soon as the more stress is applied, so this dislocation will go more, and there is one times will come when the segment of dislocation with the opposite line vector will cancel out each other. So like okay. So let's say this is my okay, let's see, Burgers vector. Okay. So this is the direction of my line vector. So here at this 2 point you can see okay, the segment of dislocation is having the opposite line vector, and so that they will cancel out each other, and finally we'll get a dislocation loop form here, and the dislocations will move ahead. Okay. Okay. So by this way, the bypassing of the precipitates will take place. So this is also known as the here we can see that the dislocations are generating. So this is also the mechanism of dislocation generation. So let me write down here. Dislocation bows between precipitates. Here segment of dislocation with opposite line vector cancel each other, and here the dislocation loop formation is taking place. Okay, so this is all about the bypassing of the precipitates. So the shear stress required to bow a dislocation is given by tau is equal to 2 alpha GB upon lambda, where lambda is nothing but the distance between the precipitates, or the this interplanar. This is the distance between the two precipitates, that is lambda. Okay, so as this we have already discussed here that here the third point, the interface between the, that is the distance between the precipitates, changes with the aging time. So the lambda, sorry, so the lambda is directly proportional to the r, the precipitate size. Okay, so the alpha, GB and all are constant, so the tau is inversely proportional to 1 upon r. So as the size of the precipitate increases, so the dislocations will try to bow. Okay, so this is about the bypassing of the precipitates. So now if we plot the graph versus graph of tau versus r for the cutting and bowing, so we'll get something like this. let's say this is my R, and here I have tau. So if we like the shear stress required for the cutting, if we see, it is increases with the increase in the R, as tau is directly proportional to root R. So this is the shear stress for cutting. Whereas for the bowing, it decreases with the increase in the R. So this is for the bowing. So if I plot the net curve, so I will get something like this. Let's say this is my net curve, and this is my critical radius. So at this the critical radius, the bowing is comparable to that of the shearing. So at this radius, both the shearing and bypassing mechanism will be active. So if in general, in overall, what we can say that the bowing around the dislocation will be preferred when the precipitate size is large. So and the second one is the at critical radius. At critical radius, bowing is comparable to shearing. It means both mechanism will be active. Both mechanism will be active. So this is about the dislocation interaction with the precipitates. Now if we plot the aging curve with the aging time, means aging curve, that is the hardness versus the aging time. So we'll get a curve something like this, aging curve. Okay. So let me plot the aging curve. So on x-axis we have the aging time t, and on y-axis we have the hardness. Okay, so we will having some hardness at t. So as the time passes, aging times, the hardness increases first. Then it starts to decrease as the precipitates are becoming bigger and bigger. So if I join these points, so I'll get a curve something like this. Okay, so at this point we have the highest hardness. So this condition is known as the peak aged condition. So And this zone is known as the underaged condition, and this zone is known as the overaged condition. Okay, so this is my highest hardness. So this point is known as the peak age condition. So if I show the precipitation sequence of the aluminum 4 weight percent copper. So here somewhere we will be getting the alpha solid solution strengthening at this point. Okay. So in this region we will be having some GP zone. Here somewhere around the peak age we will having the theta double L prime. After the this peak age has passed, we will be having some theta prime, and the 8 we have a equilibrium precipitates, that is theta. So in the underaged region, the shearing mechanism is dominant. And here in the overage condition, the bowing dominates. Okay. So what we can write, the highest hardness corresponds to the peak age condition. So highest hardness. Okay. So this is about the aging curve. Now if we see the effect of temperature on the aging curve, so let me make a partition here. So let me draw the schematic first here. Let me write down the effect of temperature on aging curve. So let's say okay, and here this is temperature, this is composition. So if I plot a aging curve, okay, so this is aging time, and here we have the hardness. Okay, so at a higher temperature, let's say this is let's say these are the three temperatures: T1, T2, and T3, such that T3 is greater than T2 is greater than T1. So at the higher temperature, the volume fraction of the precipitate decreases. So we will be having the decrease in the hardness. So and also as the temperature increases, the time to reach the peak hardness will reduce. Okay, so as I already mentioned that the for forming the precipitation earlier, to form the precipitates earlier, we heat the material, or we'll kept it at some temperature. So here we have two conditions. As the temperature increases, here you can see. Let me see. Take any composition of C naught. Okay, so here you can see as the temperature is increasing, the volume fraction of precipitate is decreasing. So, which will result in the decrease in the hardness of the material. So, if I plot all this curve here, so this is for T1. So, if I plot for T2, it will be something like this T2. And if I plot for the sorry, this will be for the T3. Oh my god, sorry, my mistake. So as the temperature is increasing, precipitate's volume fraction will decrease. So this will result in the lower hardness. So this is T3. Then we have some highest. Sorry guys. Okay. So somewhere around here we have the aging curve at a temperature T2, and if we draw for the T1, so this one will be the T1. So if we take a time to reach a peak hardness, so if we see this is T1, T2, and T3. So we can see that the T3 is greater than T2 is greater than T1, but the hardness H3 is less than H2 is less than H1. Similarly, the T3 is less than T2 is less than T1. Okay, so with increase in the temperature, the time required to reach the peak hardness has been reduced. So if I write in the short, so I can write like this. If the temperature increases, volume fraction of precipitates decreases, so which will result in the decrease in the hardness. And so if the temperature increases, the time to reach the peak hardness is decreases. So this is all about the effect of temperature on aging curve. So the question comes here, like why do we need to quench the alloy of the solution treatment and not slowly cool it? Any guesses, guys? So please think on this. Why do we need to quench the alloy after solution treatment and not to slowly cool it? Okay. So please think on this. Okay. Or at the end of this session, we'll discuss why is it so. Oh, and the second thing after this we have seen is the dispersion. Strengthening. So in dispersion strengthening, the strength is enhanced by the addition of the dispersite that is added externally. So dispersites are the hard and insoluble second phases which restrict the movement of the dislocations and by which we will get the enhancement in the strength. So let me write down. restrict the moment of dislocation. So dispersites dispersites are hard and insoluble second phases. So this is about the dispersion strengthening. So in dispersion strengthening, we are adding the second hard and insoluble second phases. So the interfaces is generally the incoherent, and as the phases are hard, they are difficult to cut. So the dislocation will bow around it. Okay. So now, if we see the differences between the precipitation strengthening and dispersion strengthening. So, what are those? Can anyone answer this? Between precipitation and dispersion strengthening. The first difference is that the precipitates are the in situ, means they form from the matrix itself, whereas the dispersites are added externally. So, precipitates are in situ, form from matrix. Okay, and the dispersites are externally added. This is one difference. The second difference is that the precipitates dissolves at higher temperature. Here, I have shown you that here at higher temperature, the precipitates are dissolving, whereas the dispersites don't dissolve at a higher temperature. So, at a higher temperature, the material with the dispersion strengthening does not lose its strength that much as compared to that of the precipitation strengthening. So for higher temperature application, so people prefer dispersion strengthener material. So like ODS steel, etc. So precipitates dissolves at higher temperature, and whereas dispersites don't dissolve at higher temperature. Okay. So this is all the things that we have seen in the last week content. That is the week 9 content. So based on this recapitulation and the concept, we'll try to solve some concept related problems. So any doubt till this point, guys? So this was the recap of week 9. So first we have seen the strengthening mechanism. So then we have seen what is strengthening, how the dislocations can interact. Then what is precipitation strengthening. Then the basic criteria for the precipitation strengthening. Then the what are the precipitation characteristics. Then what are the different types of interfaces, and these are the things we have seen. Then we have seen how these dislocations can interact with the precipitates. So in that we have seen the dislocation can cut or it can bow around the precipitates. And after this, we have seen the aging curve and the effect of temperature on the aging curve, and followed by the dispersion strengthening. Okay. So now we'll move towards solving the problems. So here comes the first problem. The problem is like that. Consider a precipitation strengthened aluminum alloy After appropriate heat treatment, the microstructure of the alloy consists of precipitates with a mean spacing of 0.2 micrometer. Compute the shear stress required for Oro1 bowing of dislocation in this material. For aluminum, we have following data. So they have given the lattice parameters, shear modulus, and alpha. So they are asking us to find out the shear stress that is required for a dislocation to bow around the precipitates. So please try to answer it, guys. So please try to answer it, guys. It's very simple. You need to use the equation tau is equal to 2 alpha gb upon lambda. So all this value has been given, alpha g and lambda. You just need to figure out how to calculate the b and you will get the answer. Okay, so let me write down what are the things has been given and what they have asked us to calculate. So they said that the precipitates are there and they are at a distance of lambda equal to 0.2 micrometer. Okay. Then they have given the lattice parameter A naught. They have given the shear modulus 30 that is equal to G, and they have given the alpha equal to 0.5. Okay. So and also they have given the aluminum alloy. So we know the aluminum is FCC, and for FCC the Burgers vector is, what is Burgers vector for FCC? It's A by 2 110 type. Okay. So if you calculate the magnitude, so A by 2 root 1 square plus 1 square plus 0. So we'll get the Burgers vector as, the lattice parameter is given as A naught by root 2. So A naught is how much? 0.4 into 10 to the power minus 9 divided by root 2. So we'll get Burgers vector as 0.28 into 10 to the power minus 9 meter. Okay. So now we got the Burgers vector. Now we need to find out the what is the shear stress. So we know tau equal to 2 alpha gb upon lambda. So we have all the values. So we'll put 2 into 0.5 into g is how much? 30 into 10 to the power 9 into Burgers vector is how much? 0.2828 into 10 to the power minus 9 divided by lambda is how much? It's given as 0.2 micrometer. So we'll convert it into the meter. So we'll get tau as 42.42 into 10 to the power 6 Pascal, or tau equal to 42.42 megapascal. So this is the answer to our first question. So any doubt like how we have calculated the Burgess vector? Okay. So now moving towards our second question. So the second question is like an aluminum copper alloy with 4 weight % copper is etched from theta precipitates CuAl2. So they are asked us to using a figure determine the volume fraction of CuAl2 and take rho L as 2.7 into 10 to the power 3 kg per meter cube. It means they have given the density of aluminum and copper, and also they have given the atomic mass of aluminum and copper, and we need to consider the temperature of 25 degrees Celsius. Okay. So now, can you determine the value fraction of CuAl2? So please try to answer it, guys. Sorry. So I'll give you the hint. First, you need to calculate the weight percentage of copper and aluminum in CuAl2. Then you need to find out the density of CuAl2, and then you need to apply a lever rule so that you can find out the weight fraction of CuAl2. And if you got the weight fraction of CuAl2, now you can convert it into the volume fraction. So now please try to solve it. Please try to answer it, guys. Did you got the answer? Okay, let's see. So they have given, first we'll write down the what are the things that has been given. Okay. So we have given the density of rho L 2.7 into 10 to the power 3 kg per meter cube. The rho of copper is 8.9 into 10 to the power 3 kg per meter cube. We have atomic mass of aluminum as 27 gram per mole, and for that of copper is 63.5 gram per mole. Okay, so now if we need to find out in CuAl2. So first we'll find out the weight percentage of copper in CuAl2. So first we'll take the Cu. The atomic mass of Cu is 63.5 divided by the total mass is how much? 63.5 of that of copper and 2 times of the aluminum, that is 27. So we'll get somewhere around 0.54 or 54 percentage. Is it not? Now if I find out now if I calculate the that for aluminum, so what I will get? The similar thing, just we need to replace it with the aluminum. So we'll get 0.46 or 46 percentage. Now we need to calculate the density of the CuAl2. So what we'll do? We'll consider the unit mass. So if we consider the unit mass, then we can write that the density of rho CuAl2 is equal to 1 upon weight fraction of copper divided by density of copper plus that of aluminum to the density of aluminum. So if we put all these value, so we'll get 1 upon WCU is how much? It's 0.54 and density of copper is how much? It's 8.9 into 10 to the power 3 plus 0.46 divided by 2.7 into 10 to the power 3. So we'll get rho CuAl2 as 4.3 into 10 to the power 3 kg per meter cube. This is the density of rho Cl2. Okay. So now consider that there is no changes between the not that much changes between the 300 degrees Celsius and 25 degrees Celsius, and assume that at this left corner, that is A, it is reaches to 0. So now if we apply the lever rule, so let me write down. Now apply the lever rule. So the weight fraction of CuAl2 is equal to, so here they have given us the 4 atomic weight percentage. So at this end we have 4 minus 0 divided by, here it is almost touching to near to the 54. So 54 minus 0, so we'll get somewhere around 0.0741. So now you have the weight fraction of the CuAl2. Now you just need to convert it into the volume fraction. So volume of CuAl2 divided by total volume. So this is how you will get the volume fraction of CuAl2. So now volume fraction of CuAl2 is equal to volume of CuAl2 divided by total volume. That is WCl2 rho CuAl2 plus Al rho CuAl2. So if I put this value, so it is 0.0741 divided by 4.3 into 10 to the power 3 whole divided by 0.0741 divided by 4.3 into 10 to the power 3 plus. Now we need to find out the weight fraction of aluminium. So it is nothing, just the 1 minus that of the CuAl2 divided by the density is how much? 2.7 into 10 to the power 3. So we'll get the volume fraction of CuAl2 as 0.048. So this is our answer. Okay, so did you got it how I solved it? Any doubts in this? So first, what we did, we calculated the weight fraction of copper and aluminum in CuAl2. Then we found out the density of CuAl2. Then we by applying the river rule, we calculated the weight fraction of CuAl2. Then we had the weight fraction, we just need to convert it into the volume fraction. So volume fraction of CuAl2 is nothing but the volume of CuAl2 divided by total volume. So we had all the values, so we put in that and we got the answer. The final answer is V means volume fraction of CuAl2 equal to 0.048. Okay, so this was the second question. So any doubt in this one? Okay, we'll move towards next question. So the next question is like this: an overaged precipitation hardenable alloy has a yield strength of 500 megapascal. So estimate the interparticle spacing in the alloy given that given that G is equal to 30 gigapascal and Burgers vector as 0.25 nanometer. Assume alpha equal to 0.5. Please try to answer it, guys. It's very simple. Okay, so we'll solve this. So what they have given, an overaged. Okay, so an overaged means we will be having the bowing of dislocation. So and they are asking us to estimate the interparticle spacing. So if it is overage and it is overage precipitate means the dislocation will bow. So equation for bowing is tau equal to 2 alpha gb upon lambda. So we need to find out what is lambda. B is given, alpha g is given, alpha is given. We don't know the value of tau. So how will calculate the tau there? So one equation, two unknown. So what are the things that has been given? That we have alpha equal to 0.5, G equal to 30 GPa, B equal to 0.25 nanometer. So we don't know the tau and we don't know the lambda. So first we need to find out the tau, then only we will be able to find out the lambda. So how we can find out the tau? Any guesses how we can calculate this tau? So we need to take a help of our previous concept, that is the von Mises and Tresca criterion. So here we have given the yield strength of the material. So we need to the stress we consider the maximum. So the maximum stress by the Tresca criterion is given by the half of its yield strength, or the sigma 1 minus sigma 2 by 2, or sigma 2 minus sigma 3 by 2, or sigma 1 minus sigma 3 by 2. Here we have only one sigma given, that is the yield strength of the material. So by Tresca criterion, tau max is equal to sigma y upon 2. So we have sigma y as 500 MPa. So 500 divided by 2. So tau max is 250 MPa. Okay. So now we have the tau max, alpha GB. So please so we can determine the value of lambda. Please tell me the value of lambda, guys. So we'll use this equation. So 250 equal to 2 into 0.5 into G is 30 into 10 to the power 9 into 0.25 into 10 to the power minus 9 divided by lambda. So lambda will be this is 250 megapascal. So if we convert it into the Pascal, we'll get 250 into 10 to the power 6. So now lambda will come out to be 30 nanometers. So this the interparticle spacing is 30 nanometer. Okay, so it's looking like a 80 nanometer. It's 30 nanometer. Okay. So now we'll move towards next question. So the question is like that. So they have given uh, the question is like that. For a unit cube containing a dispersed second phase of uniform spherical particle of radius r, the number of particles per unit volume, that is NV, is related to the volume fraction of particles F by NV equal to F upon 4 by 3 pi r cube. The average distance between particle is given by lambda equal to 1 upon uh, NV to the power 1 by 3 minus 2r. And they are asking us to prove that lambda equal to 2r 1 upon 1.91 f to the power 1 by 3 minus 1. It's a very simple question. You can answer it. Did you got the answer, guys? Okay, let's see. So they have given NV equal to F upon 4 by 3 pi r cube, and this is equation 1, and lambda equal to 1 upon NV to the power 1 by 3 minus 2 r. Okay, let's say this is equation 2. So put value of NV in equation 2. So what we will get? Lambda is equal to 1 upon NV is how much? F upon 4 by 3 pi r cube to the power 1 by 3 minus 2r. Okay, so now if we simplify it, so what we will get? So lambda equal to this r will go upside, so we'll get somewhere like 4 by 3 pi r cube to the power 1 by 3 upon f to the power 1 by 3 minus 2r. So this cube root and this 3. So we can write as lambda equal to 4 by 3 into pi to the power 1 by 3 r cube to the power 1 by 3 upon f to the power 1 by 3 minus 2r. Is it not? So this get cancelled. Okay. And here this term is there, whole term, and I need a 2r. Okay. So if I multiply and divide by the 2r, so 2 by 2. So what I get? I get equation something like this. That is lambda is equal to 2r 4 by 3 into pi to the power 1 by 3 by 2 into 1 upon f to the power 1 by 3 minus 1. Okay, if we rearrange these terms, we can write lambda is equal to 2r into 1 upon 1.91 f to the power 1 by 3 minus 1. So this is how we prove it. This is the final answer. Okay, so now move towards the next question. It's very simple. So they are asking us for an aluminium 4% copper alloy, the shear stress requires to bore the dislocation around the precipitates is 300 megapascal. Estimate the particle spacing. So they are asking us to find out the lambda, and they have given the values of G, B, and alpha. Please try to answer this, guys. Please try to answer it. So we'll try to solve it. Okay. So they have given the shear stress as 300 MPa. So tau is 300 MPa. Then they have given us the G. G as 27.6 GPa. So let me convert it into the one unit. 300 into 10 to the power 6 Pascal, or 27.6 into 10 to the power 9 Pascal. Then we have the B as 0.25 nanometer, or 0.25 into 10 to the power minus 9 meter. And we have alpha as 0.4. So now they are asking us to find out the estimate particle spacing, that is lambda. So we know the equation tau equal to 2 alpha GB upon lambda. So now you have the equation. Now tell me the answer. What is the value of lambda? So we can write lambda is equal to 2 alpha GB upon tau. So this becomes 2 into 0.4 into 27.6 into 10 to the power 9 into B is how much? B is 0.25 into 10 to the power minus 9 divided by 300 into 10 to the power 6. So we'll get lambda somewhere around 18.4 nanometer. Okay. So now here comes the next question. Sixth and seventh question. So they have given a single crystal of aluminum is deformed in a tension in 112 direction. The Schmidt factor cos lambda and cos phi for a various slip system is given below. So they are asking which slip system will be activated first. If the critical shear stress is 50 megapascal, what is the minimum tensile stress required at which material will start to deform plastically? It's very easy question. Please try to answer it, guys. Okay, so here we know that is tau is equal to sigma cos lambda into cos phi, and this is nothing but a Schmidt factor. The we know the slip system with the highest Schmidt factor will deform first. So here we have this slip plane and slip direction given, and they have given the Schmidt factor. So all out of these three, the maximum Schmidt factor is for the case C. Is it not? So the first slip system will be activated in C. So now they are asking if the critical shear stress is 50 megapascal, what is the tensile stress required at which material will start to deform plastically? So here in the first pass we know the slip system with the highest Schmidt factor will be activated first. Okay, because it will require less stress, tensile stress will be required to deform a material plastically. Okay, so similar concept we can apply in the 7, that is tau CRSS equal to sigma into m. So sigma equal to tau CRSS by m. Okay, so tau CRSS is how much? 50 megapascal divided by root 6 by 6. So sigma equal to how much? 50 into root 6, or if we convert it into the decimal value, we'll get somewhere around 122.47 megapascal. So this is just a concept based question. Okay, so now we'll see this part. Like, why do we need to quench the alloy after solution treatment and not slowly cool it? So, any guesses, guys? Okay, for your better understanding, I will draw the phase diagram, and from that you can guess, try to guess. So, if we heat the material and solution treated it, okay, like this region, in this region, okay. Sorry, guys. Let's say my composition is C naught, and I am solution treated in the. I am solution. Sorry. So we have solution treated it. Okay. So what will happen at a higher temperature? Okay. The higher temperature, the thermal kinetics will be higher, so that the B atom will get a sufficient times to come out of the alpha matrix, and it will try to precipitate out on the grain boundaries. Okay, so like this, let me show you for better understanding. So okay, so let's say this is my grain. Okay, so this is my microstructure. Let's see. So at higher temperature, okay, so at higher temperature, so the B atoms, okay, let's say this is my alpha. So the due to higher thermal conductivity, the B atom will get a sufficient time to come out from the alpha, and they will precipitate at the grain boundaries. Okay. So this is precipitates. Okay. So this precipitates. This is grain boundary. So what it will do? These precipitates will result in the intergranular fracture. Okay, so like material fail will along the grain boundary. Okay, so this will result in the intergranular fracture. Okay, so the material can easily get fractured. Okay, as its brittleness will increase. So because of that, we don't slow pull it after the solution treatment is done. So that's why we generally quench it, so that we get the precipitates inside the grain. Okay, so let's see. Let's see. And slow pulling. This is after quenching. Okay, so after quenching also we can get a precipitates at the grain boundaries, but it is not that much as that of the previous case. Okay. Okay. So that's why we'll prefer that is quenching after the solution treatment is done rather than the slow cooling. Okay, so so this is all about the week 9. Okay, so if you have any doubts till this point, you can ask, or we'll end our session here itself. So any doubt till this point, guys? So I think no doubts are there. So thank you everyone for attending the session. So in the next week, we'll try to cover the assignment 9 as well, and we'll try to take some mixed type of questions, like from what are the things from week 1 to week 10. Okay, so from each week we'll try to solve one or two type of questions, so that you will get a week recapitulation of all the week contents, so which will in turn will help you in your end exam. Okay, so next week probably we'll try to cover that, like uh, the two questions from week 1, two questions from week 2, like that, and by that way we can quickly recapitulate all the syllabus. Okay, as the end exam time is coming near. Okay, so thank you everyone. Thank you coming. Thank you for coming. So I will end today's session here itself. Okay. So last time, uh, any doubts till this point? Okay, great then. So I will end today's session here itself. Okay. Thank you everyone.